Hello, so this is my sort of introduction to the EM spectrum plus a little bit of extra information that you might want to use. So let's start with this, the electromagnetic spectrum. It's just a series of electromagnetic waves. They're all very similar to light. In fact, the only difference is the wavelength. So we have visible light that you're all familiar with, and then over to one side over here we've got radio waves, we've got microwaves, infrared, then we've got visible light in the middle, then we've got ultraviolet, X-rays, and finally gamma. Okay, so the only difference between these things is the wavelength. So with the radio waves, they have a longer wavelength, and then as we go down to this end, they get shorter, and then shorter and shorter until the gamma waves have incredibly short wavelengths. The length of one peak to the next is sort of down at the size of an atom, if not smaller, maybe the nucleus. So it's these different wavelengths that give them their different properties. One other thing that we can add to this is that as we move along this way, these ones have got more energy and these ones have got less. So because of that, that makes the ones up at this end more energetic and more dangerous. And in fact, we've got that the ultraviolet, X-rays and gamma are all ionizing. And that's really important. Ionizing, if you remember, simply means that the wave can come along, and if you've got an atom, I've drawn, there you go, a nucleus, and there's a little electron going around the outside. When the wave hits it, if it's got enough energy, and ultraviolet, X-rays and gamma have enough energy, it's able to knock the electron off of the atom. And that's important because if that happens in a living cell, there's a chance that it could kill the cell, but it could also change the way the cell works. And this could lead to cancer or to a tumour forming because it affects the way the cells divide. Now, all of these waves have a bunch of things that are in common with each other. I showed you this in class, but I'll show you here again. Okay. So here you go, here's my handy slide. So key facts that you will definitely need to know is that electromagnetic waves are all transverse waves. They can all travel in a vacuum, and sometimes that's referred to as not needing a medium. So a medium just means stuff to go through. And they all travel at the same speed. In a vacuum, that is. And that's 3 × 10⁸ meters per second, which is often referred to simply as the speed of light. And then the bit at the end is kind of stating what I've stated up here, which is the difference between the different type of waves, that they have different wavelengths, and this leads them to have different properties. Okay, so I'm now going to go through each of the waves in turn. So we'll start with radio waves. Radio waves have the longest wavelength, some sort of number of kilometers long in some situations, and they're used for radios. So they're used for communication. They can carry signals a long distance, and it's not on our specification to explain exactly how that works. But you do need to know how the signal works with an aerial. So I'll show you that in a second. So I've got a little picture. So here we go. These are 2 people with walkie-talkies. And whenever you've got a walkie-talkie or a radio, you'll always have an aerial. So when this person speaks, the sound goes into the radio. Various electronics change that into a signal that needs to be sent. And what that creates is an alternating potential difference, or an alternating current, in this metal aerial. And what that means is that the electrons in that aerial start moving up and down. And those electrons moving up and down produce the radio waves. And that signal moves up and down, matching the movement of the electrons moving up and down in the aerial. And then the signal reaches the person at the other end. And that signal hits the aerial, and it causes the electrons in that aerial to move up and down, matching the signal that was sent originally from the first radio. And then the electronics inside this radio can turn that back into sound, and this person hears it. So the way this is described in your specification is simply that oscillations in this aerial are going to produce the radio wave. I'm just going to check exactly how they phrase it. So these radio waves are produced by oscillations in this circuit. And then when the radio waves are absorbed by this aerial, that creates an alternating current with the same frequency, so going up and down the same rate as the radio wave itself. Okay, so move that out of the way. A couple of other little facts about radio waves. Well, one is they are not ionizing. Very important. Second thing about the radio waves is that we have to think about how we use them in communications. And I'll talk about that in another little bit. Okay, so next we have microwaves. Now microwaves are electromagnetic waves where the wavelength from there to there is around 10 centimeters. And it's pretty obvious what they're used for. Main one, microwave ovens. Now, the reason they're used in microwave ovens is that they cause water and fat to vibrate. And that just means they get hot. So you can use them for cooking. But the other thing that they do, and this is probably more relevant to your lives, is that they do the same thing that radio waves do. That they can basically make electrons move up and down in wires, so they can be used for communication. And they're used in two main things. One is mobile phones. So your mobile phone, if you have one, will have an antenna or an aerial, but it's inside the back of the case. You don't see it. It's not like an old-fashioned radio where it sticks up. The aerial's inside the phone. But in that, an alternating current moves backwards and forwards, and that creates microwaves. And then those microwaves hit an aerial, and it makes the electrons in that aerial move back and forth with an alternating current that has the same frequency. And that's how the communication works. But it's not just mobile phones. Another very important property of microwaves is that if you've got the planet Earth and you've got a satellite up in space and you want to communicate with the satellite, you need to find a way of sending messages back and forth. Now, you could use radio waves, but radio waves are quite long wavelength and therefore can't send much information. but it turns out that microwaves have a property where they are able to go straight through the atmosphere. And because they've got quite a high frequency and a short wavelength, they can carry lots of information. So they can pass through the atmosphere, which is useful, and carry lots of information. But generally, apart from this straight up and down to the satellites, they don't carry information, or they get absorbed more quickly or over shorter distances than the radio waves. So radio waves are better for sending information huge distances, but they can't carry as much information. Microwaves generally can carry lots more information, but get absorbed more easily, don't travel such great distances. Okay, so from microwaves, we're going to move on to infrared. Okay, so infrared, how's that used? Well, infrared is generally used for communication. But what sort of communication? Basically, if you've got a remote control, that's a terrible drawing of a remote control, and you want to change the channel on your television, it normally works by using an infrared LED, light emitting diode, and that sends a message to the TV saying to change the channels. So that's one thing it's used for. The other, more obvious, is cooking, because basically infrared is very, very good at heating things up. Just focus that. So if it's not a microwave oven, it's going to be using infrared. So toasters, what else? Just normal ovens, all use infrared. Very important again, not ionizing. Right, we will now move on to the next one. Okay, next one, visible light. Visible light is what you're used to. That's what our eyes can see. So things that can detect visible light are basically your eyes. There's a reason for this though. If you've got the sun is going to give off all different wavelengths. Okay, here on the planet Earth, we've got the atmosphere, and the atmosphere stops many of those wavelengths. But you standing down here, the wavelengths that are going to reach you are generally visible light. So most of the light that reaches the surface of the Earth from the sun is visible light, not the other wavelengths. So our eyes have evolved to be good detectors of visible light. Other things that detect visible light, stuff like cameras, that'll do. They're used in communication for things like fiber optic cables. So if you have fiber optic internet, the information is sent by flashes of light. But there's not much to say about visible light. Beyond visible light, we get to ultraviolet. So ultraviolet's interesting because, why is that ultraviolet interesting? It's interesting because it is the first of the ionizing radiations. So it is able to knock electrons off of atoms. And it's used for a couple of things. It might be used for tanning. If people want to get a suntan, you can use ultraviolet light. It's also used, though, if you're trying to detect fraud and things like that. If you've got, I don't know why I'm drawing this, but if you've got, say, a £5 note and you want to know whether it's real or not, you can actually shine, and you'll see that some shops do this, you can shine ultraviolet light on it. And when you shine the ultraviolet light on it, there are special inks inside the £5 note that glow under UV. What happens is it absorbs the ultraviolet light and gives it back off in a different wavelength that your eyes can see. And magically, like some other numbers appear on that note. And you see the same thing happen with credit cards. If you hold a credit card or a bank card under an ultraviolet light, there are secret numbers that start glowing that let you know that it's the real thing. So beyond UV, we're going to have X-rays and gamma. Now, with X-rays and gamma, a couple of little things that we need to start considering. So I'll do these ones, I'll do them separately. So here we go, X-rays and gamma. So we'll start off with the obvious thing, that X-rays are obviously used for taking X-rays or X-ray images. Now, the way that works is that you have a source, so something that gives off X-rays, and then you stand in the way. Sorry about the quality of the drawing. And the X-rays that come through here basically get transmitted by your flesh. I can't think of a better word than flesh. Transmitted by your flesh, but get absorbed by your bones. So transmitted by your flesh, absorbed by your bones. So what happens is you have a screen which might either be film or photographic film, but not very often, or sometimes, or normally now actually, a CCD, a charged couple device. And what actually happens is that the X-rays that come through here go through all your skin and your muscles and your fat and just go straight through, and they hit the CCD. And that bit is made to go black. But then the ones that hit your, now I don't know how to draw a skull, it's not very good, I'm going to draw bones, but the bits that hit your bones get absorbed, so it basically casts a shadow of your bones onto the film. Now that's a pretty awful drawing, but hopefully you get the idea. Gamma rays, which basically come from changes in the nucleus like we talked about in the previous topic, they're used for two main reasons. One, killing cancer cells. Now you have to be very careful there, because we've already said that because they're ionizing, they can actually lead to cancer, so you have to be very careful with your dose that you receive. Or they could be used for sterilizing medical equipment. So how that might work is that, say you've got something, I don't know, a syringe, which I've never really drawn before. There you go. You've got a syringe that you want to be perfectly clean. So when you manufacture it, you make it as clean as possible, you seal it inside a plastic bag. But there still might be some bacteria in here, and you want to kill those. Now the conventional way would be to heat it up, but we can't heat it up. So what we're going to do is we're going to fire gamma rays at it. The gamma rays don't heat this up, but they do kill the bacteria, leaving you with a completely sterilized syringe. Now, the reason I group these together is that for both of these, we need to consider dose. And what dose is a measure of how much radiation you receive and how likely it is to cause harm to you. It's measured in something called millisieverts. It's actually measured in something called sieverts, but a sievert's very big. And you want to minimize your exposure or minimize your dose. So for example, if you went to the doctor's and you had an X-ray, the doctor wouldn't stay in the room with you because they would not want to be exposed to the X-rays unnecessarily. You don't really want to be exposed to the X-rays, but the benefit of having the X-ray done is going to outweigh the risk of not having it done and outweigh the risk of being exposed to the X-ray. So you need to take that into account as well. So that's it for me. Thank you for sitting through this. Bye-bye.